We usually treat language models as sequence generators, next token, a straight line of text. But when a model solves a complex proof or writes functional code, is it actually thinking in a straight line? New research says no. Effective reasoning isn't a line, it is a molecule. And if you don't understand the chemistry of that molecule, you cannot train the model. Here is the cold start problem. We want models to perform long chain of thought reasoning. Naturally, we try to teach them by showing them examples, but this fails. The researchers tested 3 sources: human reasoning traces, weak instruction models, and strong reasoning models like DeepSeek R1. The human traces failed. The weak models failed. Only distilling from strong reasoning models worked. Why? Because humans reason implicitly. We skip steps, but a machine needs every logical link exposed. If the topology is hidden, the model learns nothing. The answer lies in topology. When researchers mapped the reasoning traces of strong models, they found they aren't just lists of steps. They possess a distinct molecular structure. In this framework, every logic step is an atom. The transitions between steps are chemical bonds. And just like in organic chemistry, the stability of the final answer depends entirely on the type of bond holding the atoms together. The first type of bond is deep reasoning. Think of this as the covalent bond of thought. In chemistry, covalent bonds are rigid. In reasoning, this happens when step A strictly implies step B. These form dense local clusters in the reasoning graph. In semantic space, these bonds tighten the logical volume by 22%. They are the rigid backbone that keeps the deduction from falling apart. But a rigid backbone isn't enough. Sometimes the model realizes it made a mistake 10 steps ago. This requires self-reflection. The paper maps this to hydrogen bonds. In proteins, hydrogen bonds allow long chains to fold back on themselves. In reasoning, this is a long-range link where the current step references a distant previous step to correct it. The data shows over 81% of these reflection steps reconnect to valid prior clusters. This folding is what prevents hallucination over long horizons. Finally, we have self-exploration. These are the van der Waals forces. In physics, these are weak, fluctuating attractions. In reasoning, this represents the model branching out, generating hypotheses or making weak associations to find a new path. They are low energy and temporary, but they are crucial. Without them, the model is too rigid to solve novel problems. With them, the semantic exploration space expands from 24 to 29, allowing the model to bridge gaps between isolated clusters of knowledge. You might think this is just a metaphor. It isn't. It is mathematically grounded in the transformer architecture. The researchers demonstrate an attention-energy equivalence. They show that the attention mechanism functions exactly like a Boltzmann distribution from thermodynamics. Stronger attention weights correspond to lower energy states, meaning stable bonds. When the model attends heavily to a past token, it is literally forming a high-energy logical bond. The physics of the model mirrors the physics of matter. This structural view explains why standard training fails. It introduces semantic isomers. In chemistry, isomers are molecules with the same atoms but different shapes. In AI, 2 reasoning traces can reach the same correct answer using completely different bond distributions. Isomer A uses deep deduction. Isomer B relies on heavy self-reflection. Both are valid. But if you mix them, like combining data from DeepSeek R1 and OpenAI OSS, the model crashes. It tries to average the structures, resulting in a broken, unstable molecule. This is structural competition, and it destroys learning. So, how do we fix this? The paper proposes Mole-Syn. Instead of just copying the words from a teacher model, Mole-Syn extracts the behavior transition graph, the molecular blueprint. It identifies whether the teacher is using a covalent bond or a hydrogen bond at each step. It then forces the student model to synthesize its own reasoning following that specific structural topology, rather than mimicking surface keywords. It decouples the logic from the specific words. The results are clear. Mole-Syn improves performance and stability across 6 benchmarks, but the bigger takeaway is a shift in perspective. We are moving away from viewing reasoning as a sequence of text. To build better thinkers, we have to stop training on the string of words and start training on the topology of thought.